Tolerance stack-up analysis objectives. We should ensure that parts fit together in an assembly properly, and since most of the parts manufactured are imperfect, or we can say it is not perfect, I can say like that, because we cannot produce it at its exact dimension. So we have to ensure that it fit together. And what is the level of that imperfection and variation allowed? That should be controlled as an objective when talent stack up. And if all the parts are produced at worst conditions, whether it is small side or large side of dimension, whether those parts can be assembled together, will serve the functional intention, and what are the factor that affects performance of part, whether it is variation of size or variation in position. All these questions lead to talent stack. What is a stack? We should determine or calculate the minimum and maximum distance between features or feature of sizes in a part or in an assembly. For example, here the maximum and minimum space available for the spring. And these two images can be calculated and controlled by using stack. Sealing interference. The maximum minimum squeeze of sealing and worst conditions can be calculated using stack, so that we can ensure that proper sealing interference. Clearance between parts in assembly, that can be calculated by using stack, as shown in this example. What is the importance? What are the importance of stack? Because this successful design creates a product, we should understand the nature of design. Will fit together well, will perform intended functions efficiently, whether we have enough tolerance to manufacture cost effectively, and to better understanding of tolerances assigned to a part. And if we understood that, then we can optimize the tolerances so that the cost of manufacturing can be reduced drastically. What are the advantages of a stock? We can understand the part function very clearly, and we can find out the problems at the initial stages, even before the prototype or production, during the design stage itself, so that we can optimize the tolerances to reduce the cost of manufacturing. We can reduce the time to market, result in successful design in a very short time duration, and it will definitely increase the customer satisfaction. When should you do stock? At the design stage before drawing release. It's a big thing to be projected as it is in one single slide at design stage before drawing release. There are two types of, in general, there are two types of stock. One is as shown in the left side of this image, the linear stacks and the radial stacks. The linear stacks generally comes with the dimensions, and radial stacks generally comprises of many angles in between the two sectors, positions of the holes. And there are two other types of stocks. One is part level stock, as shown in figure 1. There are uh, 3, 4, 5. These things can be optimized by using stack calculation. And assembly stock, we can find out what is the extreme minimum and maximum between the spacer and retaining washer in the assembly stocks. And what are the default conditions of stocks? We should understand this because we are calculating stocks by assuming that all the parts are at room temperature and parts are to the print because we are using drawings. No wear and tear in the part, zero deflection, no unusual conditions present in the part drawings or 3D models. Here one example that you can try out. Some of the Excel format I have given, and A to J dimensions are there. Some dimensions are not put in the exact value. You try it, you can solve it. And if any doubt, you can comment. I will provide you the answer. There are four basic steps in stack. First, we should identify the problem and choose the desired answer. Identify the stack path, perform the math. As usual, these four things I am repeating it again and again because these are very simple steps. There's a lot of steps to follow. How we are going to identify the problem? We should document the stock objective and conditions under which the stock is being calculated and label start point, end point, and direction of the stock. To document the stock objective, write a simple one sentence. For example, find the maximum minimum distance of dimension 25 between the shoulder and the left side of the groove. It's one of the concrete example of the stock objective. And list the conditions under which the stock is being calculated, temperature and specifications, whether it includes or excludes where if there is any amount of deflection of the parts and any other unusual conditions present in the stock, how we are going to present the start point and the end point. The positive and negative sign assigned to each arrow. The positive, the arrow pointing toward the end of the stock is plus. The arrow pointing away from the end point is negative. Therefore, when the end point is toward the right of the start point, the stock indicator would look like this. And there are rules for stock starting point. The axial stocks start on the left, radial stocks start on the bottom. And the stock indicator example is given here. The arrows with the positive negative signs shows the directions for the stock, and we have the stock objective and we have the start point, stock objective, and stock directions. What the answer we desire, whether we need a gap or interference between the two parts that we are interested to do the stock analysis, then we have to identify the stock path. Usually it is called a functional loop of the various parts in a chain. This loop has a number of parts in assembly, a number of linear dimensions in a part. That comprises one complete loop. That is called start path. Only we have to take the known dimensions. Here you can solve this x. Find the maximum minimum distance between shoulder and the left side of the group given all the known dimensions, and take the shortest possible chain of dimensions, and note that each distance begins where the previous one ends. Then perform the math. Add each column of numbers, check the subtotals, evaluate the answer as I have shown it in the assembly stack in the earlier Excel sheet. Now one more exercise, the exercise number 1, find the x here, or I can say find the maximum and minimum distance or group with x here by using the known dimensions as shown in the image. And again, find out the minimum and maximum distance of x in this image, which is shown it in vertical direction. Assembly starts usually it's the same as part talk. Part talk. The steps 1 through 4 needs to be followed, but based on the worst case meeting of parts assembled to stocks to be done to find the maximum minimum of the analyzed dimensions. Points to remember in assembly stocks: each part in the assembly should touch at least one part. The stock path can pass on from one part to the other through the contact point. Note this: each part should touch at least one part. Exercise 3 and 4, assembly stocks. Find out the maximum, extreme maximum in this assembly and extreme minimum in this assembly by using the known dimensions shown in the figure. Exercise is given to you. And find the x, that is the minimum and maximum distance between the edge of the hole and the edge of the flange. Exercise 6, find the gap, the minimum and maximum distance x in this assembly. And here we should understand some basic fundamentals from GD&T point of view. For internal feature of size, the virtual condition is equal to MMC, maximum material condition, minus a geometric tolerance. In this case, the internal feature hole has 10.2 as MMC and it has minus 0.3 mm tolerance. So virtual condition is equal to 9.9. For external feature of size, that is shaft, the virtual condition is MMC plus geometric tolerance. In this case, the MMC is 9.7 plus geometric tolerance 0.1 mm. So virtual condition is 9.8. Starts using runout and concentricity. See the drawing. The runout tolerance is given 0.3 mm with reference to the datum A. And how to interpret that? The axis of a circular element. Just remember that how it goes in line with the datum axis A. Here the maximum axis of offset or eccentricity 0.15 mm in any direction. That's why it is 0.3. So part surface, a circular element, perfectly round, assuming that. Half the tolerance in the left column, half the tolerance in right column. See why we have given here in this condition. The runout and concentricity has a tolerance that has 0.3 and 0.15 in both the directions, in any one direction. So add left column is always positive and right column is negative. And find the O-ring squeeze with and without GD&T. Stacks using profile or bilateral. Here the profile the profile of surface tolerance 1 mm with respect to datum A. Again, note that this tolerance varies, profile tolerance zone varies. This half is shown in the other stack column, extreme surface boundaries. This half is shown in one stack column. So half the tolerance in the left column, half the tolerance in right column. Left column is always positive, right column is always negative. Just note it, will be more fun going forward and while solving some problems. Stacks using position. Again, the position tolerance is given as shown in the left side RFS modifier. Nowadays it is not there. It's not required to mention it there. Position tolerance value and planar datums or datum at RFS. See the 0.4 dia position tolerance zone, how it looks, and has A and B shown here. From A to this set the axis 0.2 tolerance, and from A B and from the axis to the point B the 0.2 tolerance. So half the tolerance in left column, half the tolerance in right column. The left column is always positive, right column is always negative. Stacks using position with the bonus and shift. Is here MMC modifier is mentioned to this size tolerance as well as the geometric tolerance. The geometric tolerance and the datum, sorry. The size tolerance is 8.3 to 8.6, and the bonus, you see bonus how it is calculated. Bonus tolerance 0.15. The 0.9 dia position plus bonus plus shift. It's a tolerance zone or total tolerance zone. The 0.2 tolerance is the positional tolerance, and there's a shift of a 0.1 mm tolerance and bonus of 0.15 mm. Position tolerance with the bonus a shift reference chart. First we should identify the stock condition, whether it is 1 or 2, and follow the instruction in the appropriate cell in column B. If it is bonus, if the central line of the feature of size used in the stock, then enter maximum radial bonus in both columns. MMC number 2, MMC and LMC radius of the feature of size used in stock, then enter 0 bonus in the column containing the MMC radius, and enter maximum radial bonus in the column containing the LMC radius. And for shift, the condition number 1, central line of the datum used in the stock, the maximum shift in both columns, and MMC, LMC radius of the datum used in the stock, and a minimum shift in the column containing the MMC radius of the datum, MMC radius minus VC radius, and enter the shift in the column containing the LMC radius of the datum, LMC minus VC radius. The tolerance value in the left stock column will be positive and the right stock column will be negative. Notes to be read out, or you can refer it. How we can calculate the shift? The virtual condition radius is 16.0 minus 0.3 divided by 2, that is equal to 7.85. Note that it is an internal feature and its MMC is 16.0 and the geometric tolerance is 0.3 mm at maximum material condition. So you minus it, divided by 2. That is virtual condition radius. Here y divided by 2, it's radius. Okay, minimum shift. The MMC radius minus virtual condition radius. MMC radius minus virtual condition radius. The 8.0 is the MMC radius and minus 7.85 is virtual condition radius. that is equal to 0.15. The maximum shift value, LMC radius minus virtual condition radius. LMC radius minus BC radius is equal to 8.25, that is 16.5 divided by 2 minus virtual condition radius 7.85, that is equal to 0.4. So now you know how to calculate the shift values. And exercise here, find the maximum minimum distance x between the edge to the end of the path, and find a minimum maximum distance 1 between the edges of two small holes, edges of the two small holes. Starts using form controls. There are certain rules, two or true rule. If a star goes to a surface, the form of the surface must be accounted for in the stack. If a star goes through a surface, the form of the surface is automatically included in the limits of the dimension. And here the rule number 1 applies, where only a tolerance of a size is specified. The limits of size of an individual feature prescribe the extent to which variations in its geometric form as well as size are allowed. Find out x here by using true and true rules. The dimensions are given, the picture shown on the right side above, and below use true or true rules to solve x's. Adjacent and offset rules. If a star path exists in the portion of the path which is touching the meeting path, the star condition is adjacent. The stack path exists in the portion of the path which is not touching the meeting path, this stack condition is offset. Let us see stack 1, adjacent condition. The stack is being done at a location where the meeting path is touching adjacent to the surface from which the stack begins. And stack number 2, offset condition. The stack is being done at a location on the surface of the cover. Here also you can find out the maximum gap, number 1, and minimum space. See, adjacent are full tolerance in one column and zero tolerance in other column. Offset condition at full tolerance in both the columns. Now you can understand if you read it again and again, because I am reading it. Straightness applied to a feature of size. The effects of the straightness tolerance are not shown as a separate line on the stack form. The straightness effects are combined with the feature of size dimension as follows, and a virtual condition of the dimension in one star column and the LMC of the dimension in the other star column. Parallelism applied to a part feature. The reason for using parallelism, only about 10% of stars. For a star part feature with a parallelism control, only its flatness affects the star, and the parallelism control refines the orientation of the surface between the maximum and minimum limits of a dimension. Follow the steps below to find out. Use true or true rule. Again, you can refer back. Use adjacent or offset rule. Here the parallelism tolerance is given with respect to datum A. The 0.05 parallelism tolerance zone must fall between the maximum and minimum dimensions. Okay. Perpendicularity applied to a feature of size. Use a perpendicularity tolerance in a stack similar to straightness to FOS, not as a separate line on the stack form, but combined with the FOS dimension as follows. Enter the virtual condition of the dimension in one star column, enter the LMC of the dimension in other star column. Exercise here, we find out the maximum gap and minimum space. Thank you very much, and hope you would be able to solve all the problems or exercises, 8 exercises altogether, 10 exercises given in this presentation. Thank you. I'll meet you in the next presentation with the solutions to all the problems presented here. Let's understand the problem first. Thank you.